Hello everyone and welcome. In today's lecture we are going to talk about the electrostatics in a free space. Firstly, let's start by the definition of electrostatics. Electrostatics are basically a department of electromagnetism. In electrostatics, we are only interested about the electrical charge when they are not moving or when they are stationary or at rest. In electromagnetism, generally, we have four vectors that we are studying for all time. They are the vector E, which is the intensity of the electrical field, the vector D, or the density of the electrical field or the electrical displacement, B, which is the density of the magnetic field, H, which is the intensity of the magnetic field. And in electrostatics, we are only studying E vector, which is the intensity of the electrical field. So let's start by defining what is the intensity of the electrical field. So basically we know from the elementary school that like charges are attracted to each other and unlike charges repel each other. So we can conclude that if we have a big charge like this, a big positive charge like this, and if we put near to it a small positive charge, this charge is needed to be small because we don't want its electrical field to affect the electrical field generated by this big charge. So, and we call this by the discharge, okay? We will put the discharge close to this positive big charge. This small discharge is going to be repelled by this charge, as this charge is going to affect a force upon this small discharge and it's going to move it away from it or repel it. So, and the force per unit charge per unit discharge is called by the electrical field intensity. So the definition of the electrical field intensity is the force per unit charge that a small discharge, which is positive, will experience when it's placed in a region where the electrical field exists. The equation of the electrical field intensity is written in this way. Is the limit of Q approach 0 of F divided by Q, as F denotes the force of the electrical field that the discharge will experience, and it's measured by Newton. Q is the discharge that will experience the force from a bigger charge or from a surrounding electrical field, and it's measured by columns C. Okay, E is the electrical field intensity, as the force F is measured by Newton and the Q is measured by Coulomb. So the electrical field is measured by Newton per Coulomb or volt per meter. And then we are going to prove later why the electrical field is measured by volt per meter. Okay, so there's a question. Why do we put limit of Q approach 0 at the beginning of this equation? Because we want the discharge to be small, to be very small, as it's not going to affect the electrical field that it exists in. As a Q, we want Q to be small enough, but not 0. It's going to approach 0. It's very, very small, negligible. We can say it's negligible value when we compare it to the surrounding, to any surrounding electrical charge. And as a matter of fact, the electrical field, the electrical charge, cannot be 0. It's maybe greater or less. It's greater or equal to the electrical charge of the electron, which is 1.6 times 10 to the power of minus 19 coulomb, which is the smallest ever charge. And the finiteness of the electrical charge is not a problem. We want the electrical charge only to be small enough as it's not going to affect the surrounding electrical field. And this is the end. See you soon.